Welcome back. We were talking about minimal surfaces in the sixth sphere. We were giving the sixth sphere its standard almost complex structure, and with respect to that almost complex structure, we were considering the holomorphic curves in the sixth sphere. We have just observed that holomorphic curves in the sixth sphere are minimal surfaces, and so we'd like to know, a natural question to ask is, what can be said about the Jacobi spectrum of holomorphic curves in the sixth sphere? We have some results of Jim Simons, for example, and Ajiri, which hold just in general for minimal surfaces in S6, not just holomorphic curves. And we know that the first Jacobi eigenvalue is -2. We have a lower bound on the index. We have a lower bound on the nullity. And in the case of genus 0, so the case of two spheres, we have a lower bound on the multiplicity of the first Jacobi eigenvalue. And so we'd like to get more precise information, maybe using somehow the holomorphicity condition in a serious way. So the first observation to make is that if you look at Ajiri's proof, it turns out that Ajiri actually proves slightly more. His proof actually holds in general for a class of surfaces known as superminimal surfaces in even-dimensional spheres, and the point is that there's a class of holomorphic curves in S6 that are superminimal. These are precisely the Null-Torsion Holomorphic curves. So, in other words, if U is a special kind of holomorphic curve known as a Null-Torsion Holomorphic curve for any genus G, then Ajiri's proof works perfectly fine, and you get exactly the same lower bound. The multiplicity of the lowest Jacobi eigenvalue is at least the area over pi. Okay, so what is this null torsion condition? This is actually quite important, but it takes a little while to define, and that is what we're about to do. Okay, so we're going to define the null torsion condition by using a so-called holomorphic Frenet frame, and this holomorphic Frenet frame is basically very analogous to the familiar Frenet frame for curves in R3. So let's take a minute just to review that, just to make the analogy very clear. So let's say you have an immersed, oriented unit speed curve, call it alpha in R3. Okay, and let E1, E2, E3 be an oriented orthonormal frame along alpha. Okay, and we want to understand alpha, geometrically, so we're going to follow the method of moving frames, and what that means is taking our orthonormal frame, E1, E2, E3, and adapting it to the geometry of the curve. Let's do this in two steps. So the first adaptation is to arrange for E1 to be tangent, and E1 and E1 is tangent, and E2 and E3 are normal, okay, to the curve. So E2 and E3 still have the freedom to spin, and we're going to use that freedom to make a second adaptation. So the idea is we want E2 to point in the direction in which the curve is curving. So somehow E2 points in the direction of curvature. How do you do that? How do you arrange that? Well, you say that at a point S, at which the second derivative of alpha is not the zero vector, we're going to adapt frames so that E2 is in the span of alpha double prime of S, and that forces E3 to be E1 times E2. Okay, so the point is we first adapted so that E1 is tangent. We then adapted so that E2 points in the direction of the curvature, so to speak. And when you make these two adaptations, the frame you get is called a Frenet frame, and it's usually denoted by TNB. That's the classical notation for E1, E2, E3. And the point is that what you'd like to do by the method of moving frames is you take the derivative of your frame, and you express those derivatives in terms of the frame itself. When you do that, some invariants pop out. So in this case, for curves in R3, you get these two functions. You get kappa and tau, and these are both functions of the parameter S. Okay, so the derivative of TNB is this matrix valued in little SO3, not a coincidence that it's valued in little SO3, times TNB. Okay, so kappa is called the curvature of alpha. It is a second order invariant, and it's an exercise that kappa is 0 if and only if alpha is a line. So kappa is measuring the deviation from alpha just being a line. Tau is a third order invariant. It's called the torsion of the curve, Okay, and tau equals 0 if and only if alpha is a plane curve, so tau is measuring the deviation of alpha lying in a two-plane. So we'd like to ideally do the same exact thing, but for holomorphic curves in the sixth sphere. So this is what was done by Robert Bryant in the 80s, and I'm going to explain his holomorphic Frenet frame, which is extremely useful and powerful for calculations. Okay, so let's say, so this is just following Robert Bryant's paper, but I'm going to change notation quite a bit. Okay, so let U be an immersed oriented holomorphic curve in S6, and we're going to take the tangent bundle of S6, complexify it, and we're going to be interested in the 1, 0 vectors. Okay, so we're going to look at the 1, 0 vectors along sigma, and this decomposes into the tangent vectors and the normal vectors. Okay, so let's try to adapt frames to the geometry of the curve. So E1 through E6, let's let that be a special unitary local frame. And we want to get 1, 0 vectors somehow, so we cook them up like this. F1 is 1/2 times E1 minus E2. F2 is 1/2 E3 minus IE4, and F3 is 1/2 E5 minus IE6. So F1, F2, F3 are 1, 0 vectors along sigma, and we're going to adapt them to the geometry of the curve. And we're going to do that again in 2 steps. So first, we're going to arrange that F1 is in T1, 0 sigma. So F1 is tangent, and F2 and F3 are normal. Okay, so we now want to adapt F2 rather. We want F2 to somehow point in the direction of the curving of the holomorphic curve. Well, the extrinsic curving, that is. And the extrinsic curving of the holomorphic curve is measured by the second fundamental form. So we take the second fundamental form and we're going to extend it by C-linearity. And what we're going to do is this: at a point P, where the second fundamental form is non-zero, just arrange for F2 to point in the direction of the second fundamental form of F1, F1. Okay, so the set, now you may be worried, about this set of bad points, the set of points at which the second fundamental form vanishes. Well, it turns out that that set is either all of sigma, in which case you're dealing with the totally geodesic S2, and that's not very interesting, or it's a finite set. Okay, and you do have to worry a little bit about this finite set, but it turns out you can encode this finite set as a divisor on the Riemann surface sigma, and somehow you can understand this well, and it turns out not to be a problem, is the point. Anyway, F1, F2, F3 adapted in this way is going to be called an adapted frame. Okay, and so what do we do with an adapted frame? We take its derivatives and we express the derivatives in terms of the frame itself. Okay, this is what Robert Bryant did. And what you get are a version of the Frenet equations. And so it goes like this. So for any adapted local frame, F1, F2, F3, remember these are 1, 0 vectors along the surface, then when you take the covariant derivative of F1, F2, F3 with respect to the nearly Kähler connection, remember this is not the Levi-Civita connection, we're using the nearly Kähler connection because it plays better with the geometry, you get this matrix of objects, tensor product F1, F2, F3. Okay, so what's going on here? So the gammas on the diagonal, these are connection forms. Okay, that's reflecting the fact that we have some freedom in F1, F2, F3. We can, spin F1, because complex dimension 1 is real dimension 2, right? That's somehow what's happening here with this freedom given by the connection forms. Zeta is E1 plus IE2. It's a 1, 0 form. And then again, we have these suggestively named invariants. Well, they're not quite invariants, kappa and tau. I say they're not quite invariants because kappa and tau depend on the choice of frame. Okay, so kappa and tau do depend on the choice of frame, but the conditions kappa equals 0 and tau equals 0, those are well defined, independent of frame. And it turns out that kappa and tau can be encoded in a frame-independent way as holomorphic sections of some line bundle over sigma, but let's not go into that. The point is that one can give invariant meaning to kappa and tau, but we won't need that today. Okay, but the important thing here is the analogy with, curves in R3. So you can think of kappa somehow as being the curvature. It is, in fact, second order when you encode it properly. And it turns out that kappa equals 0 if and only if u is the simplest thing possible, namely the totally geodesic S2. And so similarly, we can call, again, by analogy, tau the torsion of the curve, and that's what we're going to do. We're going to say that a minimal surface is, a holomorphic curve, rather, is null torsion if tau equals 0. Okay, so what does tau equals 0 mean geometrically? I mean, you can look at this and say, well, kappa measures the rate at which F1 turns in the F2 direction. Tau measures the rate at which F2 turns in the F3 direction, much like for curves, but maybe we want something a little bit more usable. You might think that null torsion means that the holomorphic curve lies in an S4 or lies in some sort of complex surface, but neither of those end up being true. It's just simply more subtle than that. Okay, so how can we understand the null torsion condition? What does it mean? So here are a couple of ways, equivalent ways of thinking about it. So one way that ends up being useful, surprisingly, is for this project is to introduce an unusual complex structure on the normal bundle and J hat. And what you do is you just, J hat agrees with J on the principal normal. So it's the same for F2, right? In other words, it also sends E3 to E4, but we're going to switch the orientation on the binormal direction. So if we're thinking of things as a TNB frame, J hat is the same as J, it's just we've flipped the B orientation, but we've kept the N. Okay, so using this, we can have some equivalent, here are some equivalent conditions. So a holomorphic curve in S6 is null torsion. That's equivalent to d perp. That's the normal part of the Levi-Civita connection of J hat being 0. So J hat is d perp parallel. And that's also equivalent to J hat being parallel for the nabla perp. Okay, so that ends up being very useful for us. Also, it was observed by Robert Bryant in his 82 paper that being null torsion is equivalent to the binormal Gauss map. That's the map sending a point to the binormal line. Again, thinking in terms of the TNB frame, this sends a point to its B line, so to speak. So being null torsion is equivalent to this binormal Gauss map being holomorphic. Okay, and that's a very important fact because it lets us treat null torsion holomorphic curves. We can somehow lift them to holomorphic curves in CP6, and now we can apply methods of complex algebraic geometry, for example. And so Robert Bryant does exactly that and observes that by using the classical Werdinger theorem for complex curves in CP6, or just CPN in general, we see that the area of a holomorphic curve is quantized. So null torsion holomorphic curves have area equal to 4 pi times an integer d, where this integer d is simply the degree of the binormal Gauss map. Okay, and moreover, it turns out that holomorphic curves, null torsion holomorphic curves, other than the totally geodesic S2, have to be non-degenerate. So by Castelnuovo's bound, it must be the case that either d equals 1 for the totally geodesic S2, or otherwise d is at least 6. Okay. So this condition is, pretty restrictive, and so you might worry that maybe there aren't any null torsion holomorphic curves, or are there any interesting examples at all? So Bryant proves the following facts. So first, he observes that every holomorphic curve of genus 0 is automatically null torsion. Okay, and there are lots of these things. So already in the genus 0 case, we somehow have lots of null torsion holomorphic curves, and this fact is not too hard. After you basically encode the torsion as a section of some holomorphic line bundle and then use facts about holomorphic sections of bundles over CP1. Moreover, and this is more interesting, Robert proved a Weierstrass representation formula, just like for minimal surfaces in R3. There is in fact a Weierstrass representation formula for null torsion holomorphic curves in S6. Using that Weierstrass representation formula, Bryant proved a really remarkable, beautiful theorem. He proved that null torsion holomorphic curves in S6 exist in great abundance. They exist every genus occurs, and not only does every genus occur, but every conformal structure occurs. So we showed that every compact Riemann surface admits a conformal branched immersion into S6 as a null-torsion holomorphic curve. Really an amazing result. It makes use of the Weierstrass representation formula in the previous bullet point, and some pretty serious complex algebraic geometry. This fact was sharpened by Roland in his 1999 Chicago PhD thesis. He improved branched immersion to embedding. So it's really amazing. I mean, compact Riemann surfaces, every compact Riemann surface can be conformally embedded into S6 as a null-torsion holomorphic curve. So there are really, lots of these things. Okay, so given that this is a large and interesting class of holomorphic curves, again, going back to our main question, what can we say about the Jacobi spectrum of these things? So let U be an immersed orientable null-torsion holomorphic curve, genus G and area A, which we now know is quantized. It's equal to 4 pi d for some integer d. And recall that we know, again, just by taking a Giri's proof and doing essentially no modifications, that the multiplicity of the first Jacobi eigenvalue is at least the area over pi, okay, which is 4d. And so a natural question is, can we do better? Can we improve this lower bound? How far off is this bound? And what I've managed to show is that in the low genus case, when the genus is at most 6, then in fact this lower bound is an equality. Okay, the multiplicity of the first Jacobi eigenvalue is equal to the area over pi on the nose, which in turn is 4 times an integer, which is not obvious a priori. You can see from the proof of this lower bound that M1 has to be even, but that it's 4 times an integer is certainly not obvious, much less the fact that it's equal to the area over pi. So you might wonder where this strange genus at most 6 condition comes from. It comes essentially from the following fact. So Theorem A is a corollary of what I'm going to call Theorem A prime. This is what I actually prove in the paper, and this is a generalization. So here's what I actually prove. I show that there's a holomorphic line bundle. I won't say what it is in this talk, but there is a holomorphic line bundle L with 2 properties. Okay, so first of all, the multiplicity of lambda 1 has this upper bound. It's at most area over pi plus the number of holomorphic sections of L. Okay, and also, if it's the case that the genus is less than 1/2 times d plus 2, then L has no holomorphic sections at all. Finally, you can trace through some facts about the complex geometry of complex curves in CP6 and look up some facts in Griffiths and Harris, and if you do that, you'll notice that the condition G at most 6 implies G less than 1/2 times d plus 2. So putting it all together, if G is at most 6, then G is less than 1/2 times d plus 2, and if G is less than 1/2 d plus 2, then L has no holomorphic sections, so this term goes away, and that implies the Theorem A right here. Okay, I also am able to get a bound on the nullity. Okay, and this is true for all genera G. The nullity of a null-torsion holomorphic curve in S6 is at least 2D plus the Euler characteristic. Okay. So this is a nice lower bound, I think, but as I'm about to explain, this lower bound is certainly not sharp. The proof will make that very clear, and it would be nice if we could improve it. Okay, so I'd like to say a word now about just some of the ideas used in the proofs of, I guess this should be Theorem A prime and Theorem B. Okay, so I'm not going to go into too much detail here, but what we need essentially is a lower bound and an upper bound, right? So I'm going to review that. So the first idea is to equip the normal bundle of our null-torsion holomorphic curve with this strange, almost complex structure. It's given by, you take the normal J on the 6th sphere, but you flip the orientation on the binormal line. So we now have a complex vector bundle, and we'd like to make it into we'd like to have it, give it more structure. We'd like it to be a holomorphic vector bundle. So there's two natural ways in which you can make this into a holomorphic vector bundle. One way comes from using the normal part of the Levi-Civita connection, and the other way comes from the normal part of the nearly-Kähler connection. So these two connections induce different holomorphic structures on this complex vector bundle, and both are important. So if you look at Agiri's argument, he is also following an idea of Jim Simon's. He shows, essentially by modifying the formula, by just playing with the second variation of area, he shows that the first eigenspace, okay, so the eigenspace for lambda 1, that's isomorphic to the holomorphic normal vector fields, where holomorphic means holomorphic with respect to D, okay, from the Levi-Civita connection. So using this fact together with Riemann-Roch, you'll get exactly Agiri's lower bound, and that's exactly what he does. He shows this isomorphism, applies Riemann-Roch, and you get the lower bound. And so what we need to do is get this upper bound. So the idea is, well, is to use this other holomorphic structure. We're going to switch holomorphic structures and compare them. So let's consider the difference tensor S between the d-bar operator for D and the d-bar operator for nabla. So this very nice equation becomes this awful equation. And so this seems like a terrible thing to do. We've taken a nice d-bar equals 0 equation and replaced it with this horrible thing. However, a couple of miracles occur, essentially because of the nature of the null-torsion condition, together with how the null-torsion condition plays with the nearly-Kähler connection. It turns out that this is a system of equations. This system just decouples, kind of in the nicest possible way. This is explained in my paper. And I mean, it's kind of a miracle that this decouples, and then when you just look at what you get in the decoupling, you can just count the number of solutions, again using Riemann-Roch, and there's an obvious upper bound you can get. And the upper bound just happens to be exactly the area over pi plus the number of holomorphic sections for some line bundle, and that line bundle is a negative line bundle precisely when this condition holds, and that's it. So this is somehow being rewarded for using a connection that's more compatible with the geometry. That's a sketch of Theorem A. Okay, so for Theorem B concerns a nullity bound, and this is true for all genera, and so it's this bound, and so again the idea is to start by giving the normal bundle this strange complex structure J hat. And with respect to J hat, we're going to think of n sigma as, again, having a principal normal and then basically the binormal, but with the orientation flipped. Okay, so Ln is the span of F2 once we've adapted frames from before, and Lb is the span of F3. And so the main claim that gives Theorem B is this: if you restrict to those vectors in the null space for L, right? These are vectors in the null space for the Jacobi operator, and you look at those for which the d-bar operator of it lies in Ln. Okay, so this is a subspace of the null space. This subspace of the null space is isomorphic to this space of holomorphic sections. Okay, so this is the space of holomorphic sections of the line bundle k sigma star tensor Ln, where Ln is the principal normal line bundle and k sigma is the canonical line bundle consisting of 1-0 forms on sigma. And so the isomorphism is given literally just by differentiation, where you differentiate using the d-bar operator for D. And it's very clear that this map is injective. What's not so clear is that this map is well defined. In other words, this image really is holomorphic. It's not just some C infinity section, it's holomorphic. And moreover, that this map is surjective. Okay, but this is true. And once you know this fact, then, well, the nullity is the dimension of the null space. And we now know that this subspace of the null space is isomorphic to this space, and this space of holomorphic sections can be estimated using Riemann. The dimension of this space can be estimated using Riemann-Roch, and that's basically the proof. Okay, I should acknowledge that this was not an original idea on my part. This is basically a direct analog of the arguments used by Montiel and Urbano for infinitesimally holomorphic surfaces in S4. Okay, now in that case, they're working with surfaces of codimension 2. So the normal bundle is just a line bundle, whereas for us the normal bundle is a rank 2 vector bundle. And this explains why our results aren't quite as sharp. We have to consider a subspace of the null space to get what we want. And this proof also explains why this bound is not sharp. Okay, so there are several future directions that I'm currently exploring. So that are, I think, quite interesting and that I hope to report on somewhat soon. So as I mentioned earlier, holomorphic curves in S6 are precisely the links of associative cones in R7. So that makes them of great interest to G2 geometry. So when you have an associative cone, or just any sort of cone at all, what you'd like to do is perturb it or desingularize it, or just study those submanifolds that are asymptotic to that cone. So a study of the associative threefolds that are asymptotic to a cone, that's been done by Jason Lotte, and he studied their deformation theory. And his deformation theory was in terms of a very interesting formula, and it seems very likely that the theorems A and B from this talk will probably perhaps give more information about the terms in Lotte's formula for the deformation theory of asymptotically conical associatives in R7. Okay, but clarifying exactly how theorems A and B give this information is work in progress. Another natural question is this. So far we've been considering the closed case, right, that of holomorphic curves that are compact without boundary, but it's also interesting to consider holomorphic curves with boundary. There are various free boundary conditions one might consider. That's also under investigation, and hopefully work on that will appear sometime in the next few months. Finally, I'd like to advertise some interesting open questions. So one natural open question is, for null-torsion holomorphic curves in the sixth sphere, can one find a lower bound on lambda 2? This is actually what I was hoping to do originally, but I was unfortunately unsuccessful. So maybe a good place to start would be to look at the simplest example of a null-torsion holomorphic curve in the sixth sphere, the simplest non-trivial example, that is. So the simplest non-trivial example is the so-called Boruvka sphere. Okay, this was discovered a long time ago, like maybe almost 100 years ago by now, and it is the unique holomorphic curve with Gauss curvature, constant Gauss curvature 1/6. Okay, and it has a very nice explicit formula. It's just you write down the homogeneous cubic polynomials that are harmonic. Okay, there's 7 of them. And so this gives a map, a polynomial map from R3 to R7, and then you just restrict it to the 2-sphere. Okay, so this is the Boruvka sphere, and I've shown that the Boruvka sphere enjoys this bound, so the lambda 2 of the Boruvka sphere is at least -5/3, but surely someone other than me can do much better. It seems very likely that the Boruvka sphere, I don't know if we can compute the entire Jacobi spectrum, but maybe. And it would be good to do that, or at least to sort of attempt to get complete information, because that will give some indication as to what might be true about the higher eigenvalues and their multiplicities. Another interesting thing, and this is maybe the last thing I'll say, is this. So, like I said before, Agiri's arguments work more generally for a class of minimal surfaces known as superminimal surfaces in even-dimensional spheres. And so this is the lower bound that Agiri has. And an interesting question is, when do you get equality here? And it seems now that there are a bunch of cases in which you do get equality. So Agiri used Grothendieck's theorem for vector bundles over CP1 to show that in the genus 0 case, you do in fact get equality. Moreover, Montiel and Urbano's work shows that when n is 2, you get equality again. We're always assuming superminimal or infinitesimally holomorphic or something like that. Okay, and our theorem A today shows that again you get equality when n equals 3 and g is at most 6 and u is a holomorphic curve. Okay, so assuming all of that. And personally, I think that the class of, there's probably a lot more that can be said about this class of superminimal surfaces in spheres. This seems like a class for which we maybe have the potential to really understand their Jacobi spectrum a little better, and I think there's some interesting things which might be doable in the future. Finally, the last direction I'd like to advertise is this. S6, the 6-sphere, it is the simplest example of a nearly Kähler 6-manifold, right? And the nearly Kähler of S6, structure of S6, that played a crucial role in this talk. And in general, one can study the holomorphic curves in an arbitrary nearly Kähler 6-manifold. This is an interesting thing to do. It's been done by a bunch of folks. And it would be good to understand, I think, the Jacobi spectrum of holomorphic curves in that general setting. That should provide, I think, a lot of some interesting results in that direction. Just would be great. Okay, well, thanks for your attention, and hope you enjoyed the talk, and also all of the other talks in this conference. So, thanks.